Thank you for your kind introduction. Good afternoon, everyone. I'm Hiromu Saeki. I'm glad to have a chance to talk to you. Recent years, isolated DC-DC converter used in data center power supply systems are becoming increasingly powerful. Therefore, today I would like to talk about a new structure that improves converter efficiency. So now let me begin my presentation. First, the power consumption of data center is rapidly increasing now, so the data center power supply system must reduce losses. This construction is a power supply system for data center. So this is a commercial AC power supply, AC to DC converter, isolated DC-DC converter, and server computers. And these are connected by power supply line. Server computers are required low voltage as 12 voltage, and a large losses is generated. So in the future, to reduce losses in this line, this system is composed like this. Isolated DC-DC converter are located near each server computer. So this line with a large current is much shorter, and that line with a low current is much longer. And this line should be high voltage as 400 voltage to flow a low current. So requirements for isolated DC-DC converters, high step-down ratio, and high power density. For achieving these requirements, general methods are two. First method is that secondary windings are designed as one turn. This is a structure. Advantage of this method are one turn increase turns ratio and least high step down ratio. The winding length is short and conduction losses reduce. Second method is that LLC converter with a center tap transformer. Advantage of this method, voltage is varied with a turn ratio. Few parts and soft switching is easy on the primary side. Finally, rectifier passes only one switching device on the secondary side. In summary, conventional methods are sustainable for this requirement. However, by high step-down ratio, a large AC current flows on the secondary side and losses due to proximity effect increase. Achieving high power density is important to reduce these losses. So recent isolated DC-DC converter adopt interleaved winding. First, discuss about mechanism of proximity effect. This is copper wire. When AC magnetic field is changed, copper wire, eddy current is generated and current distribution is not uniform. So these losses increase. Interleaved winding can reduce these losses. Interleaved winding is this structure in which the primary and secondary windings are placed alternately. So interleaved winding cancel magnetic motive force between the winding layer and reduce these losses. So until now, circuit topology and transformer have been focused separately for this requirement, but it is wrong for this application. This structure is a converter without the primary inverter at the top and side view. This blue section is transformer, so this section has ferrite core and interleaved winding. This yellow section is rectifier circuit, so this section has switching devices and decoupling capacitor as center tap transformer. Focus on AC current flowing inside and outside the transformer. The path of AC current flowing inside the rectifier circuit is longer than the path of AC current flowing inside the transformer. And rectifier circuit section that is outside the transformer does not have primary winding. So this section is no interwinding and losses due to proximity effect increase. In summary, losses due to the proximity effect inside the rectifier circuit are not ignored. To solve this problem, previous studies, our research group's idea is that AC current should be confined inside the transformer. These are circuit schematics based on conventional idea and previous studies idea. In conventional, transformer and rectifier circuit are separate and leads to increasing losses due to proximity effect. Therefore, in previous study, the decoupling capacitor is divided into rectifier circuit in each secondary winding and make the rectifier circuit part of the winding. So, AC current flows inside each secondary winding. And outside the transformer is only DC current. That is, AC current is confined inside the transformer. To achieve previous studies idea, simple method is that integrated secondary winding and rectifier circuit. This is structure that achieves this method. So rectifier circuit move and is included in a one-turn loop of secondary winding. As a result, AC current inside the transformer reduces losses due to proximity effect. But previous study has a practical problem. This is AC current flows outside the transformer. I would like to talk about why this problem occurs. This is equivalent circuit schematics in previous studies. In center tap transformer, AC current flows with a phase difference of 180 degrees. In previous studies, the connection between decoupling capacitors is long. Therefore, one AC current flows only one decoupling capacitor. As a result, ripple voltage have a phase difference of 180 degrees. So, ripple voltage is overlaid in peak path. And Parasitic resonance occurs by capacitor C1 and C2 and parasitic inductor in connection path. Focus on this structure. Parasitic resonance occurs outside the transformer. So, a large AC current is induced outside the transformer and losses due to proximity effect increase. To summarize the story so far, the issues are two. 1. Parasitic resonance occurs. 2. A large current flows outside the transformer and losses due to proximity effect increase. So, my research goal is proposal for a transformer structure that confines AC current inside the transformer and reduces these losses. So my ideas are two. 1. Parasitic resonance is suppressed. 2. AC currents in the parallel connection line of secondary side overlap and these losses reduce. Therefore, my approach is 2. 1. Decoupling capacitor and through holes to connect capacitor are in the same position when viewed from the top and bottom surface. 2. The layout to connect through holes is invert comb layout. I would like to talk about methods of suppressing parasitic resonance. Focus on equivalent circuit schematics. Previous studies idea to convert AC current to DC current inside the transformer in each secondary winding. As a result, one AC current by center tap transformer flows only one decoupling capacitor. Ripple voltage is unbalanced and it leads to cause parasitic resonance. In contrast, the proposed idea is to also coupling the DC current inside the transformer. So one AC current flows both decoupling capacitor. So ripple voltage unbalance is resolved and parasitic resonance is suppressed. To achieve this idea, my approach is this. This is a structure that adapts my approach. So in this structure, through hose is located directly under the capacitor. It leads to minimize the connection path that its parasitic inductor is very small, and this allows the ripple voltage unbalance to be resolved. In summary, my approach can suppress parasitic resonance. Second, my idea is this. Why does this idea need? It is because this structure has rectifier circuit placed alternately. This is structure that first my idea adapt at back and top view. So through holes are located directly under the capacitor, and this is the connection capacitors with the same terminals and outside the transformer at top view. This current path is AC current flowing inside the transformer and flows outside the transformer. As a result, overlap primary and secondary current is not, and losses due to proximity effect increase. So we need this idea. To achieve this idea, my approach is this. This is structure that my second approach at the top and bottom layer on secondary winding at top view. Thick section is invert comb layered for connection both capacitor. This layer can connect the same terminals of a capacitor alternately with only through holes. And the current in the primary and secondary windings complete overlapped and reduce these losses. Here is one example of a structure that realizes my approach. So these are designed by printed circuit board. This PCB has 4 layers. First and fourth layer is secondary winding, and second and third layer is primary winding. Pink section is comp layered, and these through holes are connected between decoupling capacitor and located directly under the decoupling capacitor. This is a structure that first layer secondary winding and second layer primary winding at top of view. Focus on AC current on secondary side and primary side. AC current are overlapped and magnetic motive force cancel each other and losses due to proximity effect reduce. In summary, reducing these losses can realize with PCB. To confirm the effectiveness of proposed structure, I designed my 3 different types of prototype. Prototype is designed center tap transformer with PCB. This is a structure cross-section of prototype. Prototype is 4-layer PCB described earlier. So one-turn secondary windings are connected in parallel 3-turn primary windings are connected in series. Therefore, the turn ratio is 6:1. The prototype shares the same structure of primary winding but differ in the structure of secondary winding. Therefore, these are top-of-view first layers, that is secondary winding of prototype. Blue section is transformer, yellow section is rectifier circuit, and pink section is through-hose connection between capacitor. Left is conventional. Conventional is that rectifier circuit is that outside the transformer. Middle is previous study. Previous study is that rectifier circuit is that inside the transformer and through-hose outside the transformer. Finally, right is proposed structure. Proposed structure is that both section is inside the transformer. To confirm the effectiveness of proposed structure, this experiment evaluates copper loss in actual operation. So I measured AC resistance by using LCR meter to primary side. With one switching device is short and the other is open. And capacitance is 9.4 microfarad. This experiment circuit indicates AC current flowing during rectification. Measured frequency is 100 kHz to 1 MHz. Right is actual equipment. This is experiment results. Horizontal line is frequency and vertical line is AC resistance. Focus on around 400 kHz. AC resistance of previous studies greatly increasing by parasitic resonance. In contrast, proposed does not occur. This indicates proposed structure can suppress parasitic resonance. And focus on AC resistance at 1 MHz. Proposed is 14.3% less than conventional. This reduction is by rectifier circuit integrated winding. In summary, proposed structure achieves rectifier circuit integrated winding with suppressed parasitic resonance. This is summary above. Thank you for listening.